Welcome, curious minds, to another deep dive. Today, we're going to pull back the curtain on something absolutely fundamental to our modern world, something we interact with constantly, yet often take completely for granted: electricity. Think about it. You flip a switch, the light comes on, your phone charges effortlessly, the coffee maker brews your morning cup. It all just, well, it just works. But there's a whole unseen world of power beyond what simply lights up our homes. Have you ever paused to truly consider how massive factories hum with power, how towering office buildings stay brilliantly lit, or how huge industrial machinery operates with such incredible, smooth precision? You've likely heard the term three-phase power before, maybe in a meeting, or seen it referenced on a circuit breaker. It sounds a bit more complicated, doesn't it? Three phases. Why three? Why not just one, like the outlets we have in our houses? What's the big deal? And, why don't we all have it? It can feel a bit intimidating, like a concept reserved only for engineers. But whether you're someone who's simply fascinated by how big buildings get their incredible power, or maybe you're prepping for a meeting where industrial machinery will be discussed, or perhaps you just love that satisfying aha moment when a complex idea suddenly clicks into place, then this deep dive is absolutely for you. Our mission today is to break down this vital yet often misunderstood backbone of modern power distribution, specifically for you, the beginner, so you can truly grasp its elegance and importance.
That's exactly right. Our goal in this deep dive, drawing from the excellent and remarkably accessible insights found in Jonjan Koga by John Byon Cole, is to genuinely demystify three-phase power. We want to unpack its core principles, exploring why it has become the ubiquitous system for large-scale electricity use. And the critical point here is that we're going to explain it all at a beginner's level, ensuring it's completely accessible, never overwhelming, and ultimately deeply satisfying. We want you to walk away from this feeling truly informed and perhaps even, a little excited about something that might have seemed incredibly complex just moments ago.
That's precisely what we aim for. Okay, let's get right to it then. We're going to unravel the layers and get to the very core of why this seemingly intricate system is actually incredibly smart, remarkably efficient, and surprisingly elegant in its design. Let's begin with the absolute fundamentals. What is three-phase power at its most basic level?
Okay. At its most fundamental, three-phase power refers to a type of alternating current, or AC, electrical circuit, that, as the name suggests, uses three distinct wires to carry the live current. This immediately sets it apart from the single-phase power that we're all, accustomed to in our homes.
Right, the standard wall outlet.
Exactly. In a typical residential setup, you'll generally find two wires coming into an outlet. One is the hot wire carrying the active current, and the other is a neutral wire that acts as the return path, completing the circuit. Three-phase power, by contrast, introduces a third live wire, creating a fundamentally different architecture for power delivery.
So 3 live wires instead of 1.
Precisely. Now, when we talk about these three distinct phases, you might hear them referred to in a few different ways, which can sometimes be a source of initial confusion. They're very commonly called A phase, B phase, and C phase.
Okay, ABC. Simple enough.
Yeah, or especially in industrial settings, you might see them labeled as L1, L2, and L3. L4 line, presumably.
L1, L2, L3.
Right. It's important to understand right away that these are merely different conventions or naming systems. They all refer to the exact same thing: three separate but perfectly synchronized power lines, each carrying alternating current. So if you're ever in a conversation and someone says L1 and another says A phase, you'll know they're both referring to one of the three live electrical lines within a three-phase system. It's just like calling a street by its common name versus its official government designation.
Got it. Just different labels for the same 3 things.
Exactly. Now, here's where it truly gets fascinating and where the genius of three-phase power really lies. These 3 phases are not delivering their power at the exact same moment in time.
Ah, okay. Not all at once.
Not at all. This is the defining characteristic. Instead, they are precisely offset from each other by 120 degrees electrically. This phase difference is absolutely crucial to the system's incredible efficiency and effectiveness.
120 degrees. Okay, what does that mean in, practical terms? Why the offset?
It's a great question. To give you a beginner-friendly analogy, imagine 3 people trying to push a very heavy merry-go-round.
Okay, I'm picturing it.
If all 3 of them pushed at the exact same instant, the motion would be incredibly jerky, wouldn't it? Almost a series of violent stop-starts.
Yeah. Clunky. Not smooth.
Not smooth at all. And it would require a lot of effort for minimal continuous motion. But now, picture them pushing one after another, perfectly spaced out in their effort. So just as one person's push begins to wane, the next person's push is already starting to pick up, and then the third follows in perfect sequence.
Ah, like a coordinated team effort?
Precisely. The merry-go-round would spin smoothly, consistently, and with continuous momentum, without any jerks or interruptions. That 120-degree offset in three-phase power is exactly like that perfect coordinated timing. Each phase hits its peak voltage at a different moment, ensuring that as one phase's voltage momentarily dips to zero, as it naturally does during the alternating current cycle, another phase is already providing substantial power, picking up the slack, so to speak.
That merry-go-round analogy really clarifies it. It's like a perfectly choreographed, continuous dance of electricity. Okay, so what does this constant, uninterrupted power delivery mean in practical terms for the equipment that uses it?
It means you get a remarkably continuous and uninterrupted flow of power. You see, in a single-phase AC system, the voltage and current actually pass through 0 volts twice in every single cycle.
Twice per cycle, okay.
Yeah, for very small loads, like a simple light bulb or a phone charger, this momentary drop to 0 isn't noticeable at all. The light just appears to stay on, and your phone charges. Your eye can't detect it, the device doesn't care. However, for large, power-hungry equipment, especially industrial motors that need constant power to spin smoothly and continuously, those momentary drops to 0 in a single-phase system can cause, well, problems.
Like what kind of problems?
They can cause jerky operations, significant vibrations, they can reduce efficiency, and sometimes they even necessitate extra often expensive components just to smooth out the power delivery or help the motor start spinning in the first place.
Ah, okay. So single phase isn't ideal for the big stuff.
Not really. The continuous nature of three-phase power, thanks to that clever 120-degree offset, provides a much smoother, more consistent, and more powerful delivery of electricity. It's exactly what large, demanding machinery requires. It's the difference between trying to paddle a canoe by yourself, which is inherently a bit jerky, versus having three perfectly synchronized paddlers pushing you along smoothly and powerfully.
That makes perfect sense. The smooth, continuous power is key for big machines. So, sticking with the practical side, let's talk about how this power actually gets connected to, the vast majority of commercial and industrial buildings, because there's a very common method you mentioned in the prep called the three-phase four-wire connection, or 3-4-in as it's known in Korea. What's that about?
Yes. This is arguably the most common and versatile way you'll encounter three-phase power being utilized beyond the power plant itself. It's how it gets into most non-residential buildings. As the name suggests, it involves those three live power lines we just discussed, A phase, B phase, and C phase.
Or L1, L2, L3.
Exactly, or L1, L2, L3 plus a fourth wire. And this fourth wire is the neutral line.
Okay, so 3 live ones and a neutral. 4 total.
That's it. The neutral line is, as its name implies, electrically neutral. It's typically at or very close to 0 volts relative to ground, and it acts as a common return path for all three phases. It provides a stable reference point for the entire electrical system.
A return path and reference. Got it. Now, where do you typically see this system in the real world? You said not in homes.
Yeah, it's crucial to understand that this connection method is almost never found in typical residential homes. Our houses, with their everyday appliances like toasters, TVs, and refrigerators, they simply don't demand that much power or that level of electrical sophistication. However, for, as the source puts it, almost all buildings or structures that consume significantly more power than a typical house, this three-phase, four-wire connection method is the undisputed standard. Think about it. Towering office buildings in any city skyline, sprawling factories humming with machinery, large commercial complexes like shopping malls, hospitals that require unwavering power for life support.
Data centers.
Data centers, absolutely, which can never go down. Universities, large apartment buildings, they all rely on this three-phase, four-wire connection to meet their massive and diverse power needs.
And for our listeners, you mentioned a fantastic visual cue to spot this in the real world is simply to observe, now that you know what to look for. If you ever look at a main circuit breaker panel, perhaps in a commercial building, or if you're working in an industrial setting, or even maybe in the basement of a large apartment complex, and you see 3 thick power lines and 1 neutral line coming into that main breaker,
you are definitively looking at a 3-phase, 4-wire system in action. It's often right there, hiding in plain sight, powering the very infrastructure around you.
Absolutely. And here's where we get to a truly clever advantage, a real aha moment for learners about the three-phase, four-wire system. It possesses the unique ability to deliver 2 different voltages from a single connection.
2 voltages.
from one connection. How does that work?
It's incredibly versatile, a major reason for its widespread adoption. For instance, in the example system we're drawing from, if you measure the voltage between any two of the live power lines, say from A phase to B phase or B phase to C phase or A phase to C phase, you'll find a higher voltage, specifically 380 volts in that example.
380 V between any two live wires. Okay.
Right. This higher voltage is perfectly suited for heavy-duty industrial machinery, powerful motors, large HVAC systems, things that need a lot of electrical force to operate. But then, and this is the ingenious part, if you measure the voltage between any single power line and the neutral line, for instance, from A phase to neutral or B phase to neutral or C phase to neutral, you get a lower voltage. In this example, 220 volts.
Ah, so between a live wire and the neutral, it's 220 V.
Exactly. And this 220 V is the voltage commonly used for many everyday appliances, standard lighting circuits, computers, and general-purpose outlets within a commercial or industrial building. So if you need 220 V power for office equipment, lighting, or smaller motors, you simply connect one of the power lines and the neutral line to a lower-level circuit breaker within the building's electrical distribution system.
That's truly fascinating. So if I'm understanding this correctly, this single distribution system coming into a large building can efficiently provide two distinct and widely used voltage levels at once. 380 V for the big stuff, 220 V for the regular stuff.
You got it. It's like getting two different types of water from one tap. As you said, maybe high pressure for cleaning and regular pressure for drinking, all from the same main supply.
That flexibility must streamline the entire electrical infrastructure for commercial and industrial use immensely. What kind of applications does that enable within a single building?
Precisely. It simplifies the internal wiring and distribution within a building while offering the flexibility needed for incredibly diverse power demands. Think of a large hospital, for example.
Okay.
They need that 380 V for their massive HVAC systems, maybe their powerful diagnostic imaging machines like MRIs or CT scanners, and large elevator motors, big power users. But they also need the 220 V for all the regular lighting in patient rooms, computers at nurse stations, medical instruments, staff offices, you name it.
Right, the everyday stuff.
Exactly. This three-phase, four-wire system allows them to run both types of equipment from one central service entrance, significantly reducing the complexity and cost of their electrical infrastructure compared to needing, say, completely separate systems for different voltage needs. It's a testament to the intelligent and highly practical design behind this system.
Okay, wow. So we've clearly established what three-phase power is and how it's commonly connected to buildings using that four-wire system to get two voltages. Super useful, but to truly understand its magic, we need to go back to its source, literally. How is this ingenious system actually born? What's the fundamental principle at play in those enormous power plants that create this special kind of electricity?
Yeah, let's delve into the basic principle of electricity generation, which is essentially what happens inside every major power plant around the globe, more or less. Imagine the core of a generator. Within its stationary part, called the stator, which is simply the non-moving outer casing of the generator, there are three separate coils of wire.
Okay, three coils inside the stator.
Correct. And crucially, these coils are not arranged randomly. They are wound around the stator with a precise 120-degree physical difference from each other. Visualize them as being equally spaced around a central point, just like the segments of a pie.
Or the merry-go-round pushers.
Or exactly like those three people pushing the merry-go-round from our earlier analogy. That 120-degree spacing is key. Now, to form the connections, you take one end of each of these three coils and connect them all together at a single common point.
Okay, tie one end of each coil together.
Yep. This connected point effectively becomes the electrically neutral line. It's the common reference for the system.
So that's where the neutral wire comes from.
That's where it originates, yes. Then the other end of each of those three coils becomes one of your three distinct live power lines, what we call the A phase, B phase, and C phase. So right at the point of generation, you effectively have three outgoing power lines and one common neutral line, which directly forms our familiar three-phase, four-wire system structure.
Amazing. It's built right into the generator design. So what makes the electricity actually flow?
Right. The magic, as you put it, happens when a powerful magnet or an electromagnet rotates continuously within the very center of these precisely arranged coils.
A spinning magnet inside the coil.
Exactly. As this magnet spins at incredible speeds, its magnetic field cuts through each of the three coils. This action, called electromagnetic induction, a fundamental principle discovered by Faraday, induces an electrical current and voltage in each coil. And because the coils are physically spaced 120 degrees apart, the current and voltage induced in each coil will naturally be 120 degrees out of phase with each other. It's a direct consequence of the physical arrangement and the rotation.
So the physical spacing creates the electrical timing offset.
Precisely. This continuous, synchronized rotation of the magnet produces those distinct offset electrical waves that perfectly define three-phase power. You can think of the rotating magnet as the incredibly powerful engine that pushes out those three waves of electricity, perfectly timed, one after the other, ensuring that continuous smooth flow we talked about earlier.
So it's this ingenious and incredibly precise arrangement of coils spaced 120 degrees apart and a rapidly rotating magnet that literally creates those three perfectly timed waves of power. And this isn't just a theoretical model you're describing, is it? This basic principle is actually how electricity is generated on a colossal scale in the largest power stations in the world.
Oh, absolutely. This fundamental principle is precisely how electricity is generated on a massive scale in every major power plant, regardless of its primary energy source.
Sure.
Whether it's a colossal hydroelectric dam, harnessing the immense force of falling water to spin massive turbines connected to these generators,
Right.
or a thermal power plant, burning coal, natural gas, or biomass to produce high-pressure steam that drives turbines. Or a nuclear power facility, using controlled fission to generate heat, make steam, and spin turbines. The core mechanism for producing the electricity involves gigantic three-phase generators built on this very design. The scale of these generators is truly immense. Some are the size of a small house, capable of powering entire cities. But the underlying physics, that 120-degree phase separation created by the spaced coils and the rotating magnetic field, remain exactly the same.
Wow. And the visual evidence of this system is literally all around us if you know where to look, right?
It really is.
When you're driving down a highway, look up at those towering steel transmission line structures. You'll almost always see three main thick wires grouped together, sometimes maybe with a smaller ground wire running along the very top for lightning protection. That grouping of three wires is the unmistakable physical representation of three-phase power being supplied across vast distances, often hundreds of miles, from the power plant to your city or region.
Exactly. That's it in transit.
Similarly, as we mentioned, inside the main distribution panels of larger buildings, you'll see those three wires, often color-coded or labeled L1, L2, L3, bringing that enormous power supply right to the building's doorstep.
Yep.
It's that direct, tangible connection between the complex physics we're describing and the very real, visible infrastructure that powers our entire modern world. It really makes you appreciate the engineering marvels we often just drive past without a second thought.
It certainly does.
Okay, so we now have a solid understanding of what three-phase power is, those three offset waves, and how it's generated with the coils and magnet, and how it gets into buildings with the four-wire system. Now comes a really crucial question, the why. Why do we bother with three-phase power? If single-phase works perfectly well for our homes, why introduce something that seems more complex and requires more wires? What are the monumental advantages that make it the industry standard for virtually everything big and powerful?
That's an excellent and very logical question, and it truly gets to the heart of the matter. While single-phase power is indeed economical and perfectly suitable for the relatively small scale, often intermittent electricity needs of a typical household, powering your toaster for a minute, your TV for a few hours, your lights, a small appliance.
Right. Our needs are pretty modest, relatively speaking.
Exactly. It simply isn't efficient or robust enough for the colossal demands of industrial, commercial, and large-scale power supply. For those applications, three-phase power isn't just better. It's significantly more efficient, more reliable, and crucially, far more economical in the long run.
More economical, even with more wires. How does that work?
Well, one of the core game-changing benefits lies in the economic transport of power. Three-phase AC allows for the transmission of truly enormous amounts of power with a lower current compared to transmitting the exact same amount of power using a single-phase system.
Lower current for the same power. Okay,
Yeah.
why is lower current so vital?
Because when electricity flows through any wire, some energy is inevitably lost as heat due to the wire's inherent electrical resistance. It's just physics. Think of an old incandescent light bulb getting hot that's resistance converting electrical energy to heat.
Right, wasted energy.
Exactly. And this heat loss isn't linear. It's actually proportional to the square of the current. The formula is power loss equals current squared times resistance, or plus equals IIRR.
I squared R. Okay, so the current has a huge impact.
A huge impact. So even a small reduction in the current can lead to a significant disproportionate decrease in wasted energy. Think of it like this. If you somehow manage to cut the current in half, The energy lost as heat wouldn't just halve, it would drop to 1/4 of what it was.
Wow, that's a massive difference.
It is. Therefore, lower current means drastically less energy lost as heat in the transmission lines as electricity travels, often for hundreds or thousands of miles, from the power plant to your building. This directly translates to massively more efficient and critically more economical power delivery over vast distances. And, as an additional bonus for system flexibility, three-phase power can also be easily converted down into single-phase power when needed, using transformers, offering remarkable versatility within a larger network.
That's a truly profound insight about the I-squared-R loss. The natural thought for many learners, including myself initially, is, okay, 3 phases means 3 live wires, maybe even 4 with the neutral. That sounds like more materials, more complexity, more initial cost for installation.
It's a common first thought.
So why do we bother?
Yeah.
But what you're saying is that despite seemingly needing more stuff up front, it actually becomes dramatically more economical and efficient for large-scale applications because of that reduced current and heat loss.
That's a huge part of it, yes. Let's really unpack those specific advantages further. What are the key reasons three-phase power reigns supreme in our industrial and commercial world? The source highlights 3 main ones.
Okay, let's hear them.
The first key benefit is what's called easy system interconnection, or DAL MECA.
Easy system interconnection. What does that mean?
It means that the electricity generated at virtually every major power plant, whether it's hydroelectric, thermal, or nuclear, is predominantly created in a three-phase form, as we just discussed. And here's the crucial part. It maintains this three-phase form throughout its entire journey across the grid, from generation to long-distance transmission over those towering lines, then through local distribution networks using transformers, and right up to the user's building or facility, the electricity remains fundamentally three-phase.
So it stays in the same format the whole way.
Essentially, yes. This consistent form of electricity, from its creation all the way to its point of use, immensely simplifies the design, manufacturing, and configuration of all the various electrical devices and systems across the entire power grid. It's like having a universal language for electricity, as we touched on, because everything from the largest transformers in a substation to the motors in a factory are designed with three-phase power in mind. The entire system integrates seamlessly.
So less need for conversion or complicated interfaces.
Exactly. There are fewer conversion points needed, less complexity in matching power types, and generally a more streamlined, reliable flow of energy across the grid. This consistency makes the whole interconnected power system much more robust, easier to manage, and more predictable. Imagine if different parts of the internet used completely different communication protocols. It would be chaos. Three-phase power provides that unified, consistent standard for bulk power.
That makes a lot of sense. If everyone's speaking the same electrical language, so to speak, then everything just works together better, from the generator to the machine using the power. Okay, what's the next big, compelling advantage?
The second major advantage, directly addressing your earlier point about cost and efficiency, is its high efficiency for large loads, or Awastup Guroaya, high efficiency for large loads. Okay, when you're talking about large industrial operations, sprawling commercial buildings, or infrastructure like electric train systems, you're not just running a few light bulbs. You're dealing with immense continuous power consumption, huge amounts of energy. Using a lot of electricity inherently means a very high current needs to flow. And for that much current to flow efficiently and safely, the voltage needs to be proportionally higher. Three-phase systems are inherently much better at handling these incredibly high power demands, both in terms of voltage and current.
Right, they're built for heavy lifting.
Precisely. But here's where the economic win truly shines, which directly answers that initial thought about more wires, more cost. Listen to this because it's quite remarkable. Compared to a single-phase, two-wire system, a three-phase, four-wire system, believe it or not, requires approximately 33.3%, or about one-third less conductive material, meaning less copper or aluminum wire, to transmit the exact same amount of power over the same distance at the same voltage and efficiency level.
Wait, say that again? 1/3 less wire, even though it uses more wires in the circuit?
Yes. It seems counterintuitive, doesn't it? But because of the way the phases share the load and the return path, especially with the neutral and a balanced system, you need less conductor cross-sectional area overall to carry the same total power compared to shoving all that power down just one or two wires in a single-phase system.
Wow, okay, my mind is slightly blown. 1/3 less material.
Think about the implications of that for a moment. You can send significantly more power using a substantially reduced amount of expensive copper or aluminum for your wiring infrastructure. This translates into literally billions, probably trillions globally, of dollars in material and cost savings, not just in the initial setup of vast transmission lines that span continents, but also in the ongoing maintenance, repair, and overall efficiency of the entire global power distribution network.
And less material means less environmental impact, too.
Absolutely. It's an enormous environmental benefit as well, reducing the need for mining and processing raw materials. This single fact alone, the material savings for the same power delivery, is a monumental reason why three-phase power became the bedrock of industrial civilization and large-scale power grids.
Wow, that's not just a huge economic benefit, it's a colossal one. 1/3 less wire for the same power. That's truly a game changer for large-scale infrastructure. I can absolutely see why it became the global standard just based on that. Okay, and what's the third major advantage that solidifies its dominance?
The third advantage is particularly compelling when you consider the pervasive and fundamental role of electric motors in our world. It makes it easy to obtain a rotating magnetic field for motors, or Klokogueno,
Okay, easier to get motors spinning, basically. And to put that into immediate perspective for our listener, when we talk about motor loads, we're talking about an absolutely massive portion of our total electrical consumption, right?
Oh, easily.
Yeah.
Think about it. More than half of the electrical loads around us globally are motor loads. It's staggering.
This includes everything from the gargantuan industrial pumps moving water or chemicals in factories, to the immense conveyor belts transporting goods in warehouses, to the giant compressors and large air conditioning units that cool entire skyscrapers.
Elevators, escalators.
Escalators, elevators, machine tools, fans, even the tiny fan that keeps your computer from overheating, though that's usually single phase. But the big stuff, yeah, motors are truly everywhere, silently doing the heavy lifting in our modern society.
Exactly. And this is precisely where three-phase power truly shines, offering unparalleled benefits. For electric motors that need to produce continuous, powerful rotational motion or torque, the technical term for rotational force three-phase power provides far more favorable and inherently efficient conditions for generating that powerful, smooth rotating force compared to single-phase.
How so? What's the difference for the motor itself?
Well, remember how in a single-phase motor, the power dips to zero twice per cycle?
Yeah, the jerky power delivery.
Right. Because of that, the magnetic field it creates inside the motor isn't continuously rotating in a smooth way. This means you often need additional components, like a starting capacitor or a special starting winding, just to trick the motor into starting to spin in the right direction and overcome that initial inertia. And even then, their operation can be less smooth, potentially noisier, and generally less efficient, especially for larger sizes.
Okay, so single-phase motors need extra help to get going and aren't as smooth.
Correct. But with three-phase power, because you have those three current waves consistently offset by 120 degrees flowing into the motor's windings, which are also spaced appropriately, they naturally create a continuously rotating magnetic field within the motor itself. It's an inherent property of the three-phase supply interacting with the motor's design.
Ah, so the rotating field happens automatically.
Pretty much. This means three-phase motors are inherently self-starting seal. You apply power, they just start spinning smoothly. They run incredibly smoothly with minimal vibration compared to single-phase equivalents. They are far more powerful for their physical size and weight, meaning you get more bang for your buck or more power per kilogram, and they're significantly more efficient, especially under continuous load, than their single-phase counterparts.
So better starting, smoother running, more power, higher efficiency. Sounds like a win all around for motors.
It really is.
Yeah.
So using three-phase motors is hugely beneficial for any equipment that needs this kind of reliable, continuous rotational power, whether it's powering a massive pump in a water treatment plant, driving a production line in a factory, or moving people up a skyscraper in an elevator. This inherent advantage simplifies the motor design. No need for complex starting circuits, improves the reliability, and dramatically enhances the efficiency of powerful motors across all industries. This is why you'll find three-phase motors powering almost everything heavy-duty that spins or moves large loads.
Okay, that paints a really clear picture. So to quickly bring it all together for our listener, three-phase power is absolutely essential because, first, it's fundamentally how power is generated on a massive scale, whether it's from a hydroelectric dam or a nuclear plant using those spaced coils and magnets.
Yep, that's where it starts.
Second, It's incredibly efficient for moving enormous amounts of electricity over vast distances, saving about a third of the wire material compared to single phase for the same power, which is a huge economic and environmental win, largely thanks to lower current and reduced I-squared-R losses.
Crucial point, yes, the efficiency of transmission.
And third, it's perfectly suited for powering the countless motors that run our modern industrial and commercial world, providing a smooth, powerful, efficient, and self-starting rotation that single-phase just can't match for big jobs.
Exactly. Makes motors simpler and better.
All of this while being versatile enough, thanks to that four-wire system, to provide different voltage levels like 380V and 220V from a single connection point. It's a true unsung hero of the modern age, isn't it?
Indeed. Unsung is a good word for it. Understanding this invisible but absolutely critical infrastructure helps us all appreciate the sheer complexity, the incredible ingenuity, and the sheer scale behind the power that truly fuels our daily lives and our global industries. It's not just knowledge reserved for engineers or electricians, it's fundamental to understanding the very backbone of the world around us and how it operates. When you flip that light switch, there's an entire system of coordinated electrical forces working in harmony, generated potentially hundreds of miles away, all thanks to these principles.
Absolutely. It truly is one of those foundational pieces of knowledge that, once you grasp it, makes so many other things click into place about how our world functions. We've explored how three-phase power silently underpins our entire industrial and commercial world, enabling things we often just take for granted. So, here's a thought for you to mull over after this deep dive. We've now uncovered the ingenious design behind three-phase power, which is everywhere but often invisible. What other invisible but absolutely vital infrastructures in our daily lives might be equally fascinating and impactful if we took a moment to understand their underlying principles?
That's a good question.
Perhaps the intricate workings of the internet's physical infrastructure, the complex journey of our water supply from source to tap, or maybe the invisible algorithms and control systems that manage our transportation networks, like air traffic control or city traffic lights.
Lots to explore there.
We encourage you to stay curious, keep asking why, and keep seeking out those deep dives into the seemingly mundane yet truly extraordinary aspects of the world around you.